Yes, I'm thinking about theme music for this. What would be the Heat Is On by the famous East Coast band Earth, Wind and Fire. The heat is on. Anyway, the heat is on. It's on. Latent heat is on. Or it's off. What is latent heat? It's the heat needed to melt something or to boil it. If you look at a temperature chart as things heat up, there's a plateau where things are melting and another one where things are boiling. This isn't because, they stopped taking heat in. It's because all the heat that's taken in is being used to turn it from a solid into a liquid or from a liquid into a gas. And the heat needed to do this is called latent heat. Here's the same diagram with a bit more detail and some maths added. Obviously you go solid, melting, liquid, boiling, gas. That seems quite obvious. And when you are sort of just heating it up, you use the formula E equals mc delta theta. There you are, which is one you're familiar with. But when you are merely attempting to melt it or boil it, then you just have the ml, which is at the bottom there. There you go. E equals ml. And it just means that you use different formulas and different ideas for different parts of the heating process, because some of them are containing latent heat and some of them aren't. And on to my favourite topic, the refrigerator. The only thing which is more important to refrigerate to modern life really is the washing machine. The washing machine lets ladies go out to work. I shouldn't really call them ladies, should I? I mean, this is what is it, 2020? I don't know anyway, women. Lets women go out to work in a way it didn't before because there was the sexist conditions existed at the time. Now we should all do our own washing. Is that all right to get out of that one? My daughters will find out about this. Anyway, the refrigerator. Well, how does the refrigerator work? It works by latent heat. Gas, which is allowed to expand into a wide tube inside the fridge, it becomes gas, turns from liquid to gas, boils. And the boiling takes heat from the food. Then it gets to the bottom of the fridge where it's compressed back into a liquid again. And as it goes into a liquid, it then has to get rid of all its heat, get rid of all the heat that was in it, so that it can turn back into a liquid, and it's then allowed to expand back into a gas again, hence the circular motion of this process. And latent heat is really the answer, because it's latent heat being taken in from the food, which cools it down. And now to a less favourite topic, storage heaters, old-fashioned lumps of concrete sat in the corner of your room, wrapped in a tin box and called a heating system. Basically, cheap electricity at night would heat them up and they would cool down during the day. So all the time when you didn't need it, the house was lovely and warm, and you got home in the evening, you had to turn the fire on. Completely useless. But there were storage heaters. There was concrete because they have a very large heat capacity. The bricks would store a lot of heat and then release it very slowly. We still talk about this because sometimes architects who think about things put large lumps of concrete right behind windows so that they'll cool the building down by absorbing the heat from the sun during the day, but keep it warm during the night as they slowly release the heat. It's actually quite clever. But the electric ones, a bit of a waste really now. So, what is heat capacity? Well, it's the amount of heat it takes to, increase the temperature by 1 degree Celsius or 1 degree Kelvin. So that's the heat capacity. So the whole tank, the whole thing, that has a heat capacity, whereas 1 kilo of the water inside it, that has a specific heat capacity. Specific means 1 kilo of it, whereas heat capacity means the whole thing. So the heat capacity of a boiler is different from a kettle, but the heat capacity, specific heat capacity, is the same because it's the same kilo. So boiler, kettle, exactly the same. If you've got the specific heat capacity of 1 kilo. So it's the amount of heat energy to raise 1 kilogram by 1 degree. And we can use it in a calculation. Q equals mc delta theta, where the C is the specific heat capacity. And we remember that, if we can, to help us find or define it. The actual formula, of course, logbook. And this is the use of it, 2 kilograms by 30 degrees, put in the 2 kilograms, 30 degrees, and the figure you're given for specific heat capacity, and you get an answer. Quite a lot of joules, Nowhere near as many joules as if you're heating up water for a lot more. This is water being heated up by 80 degrees, because water has a much larger specific heat capacity. This is why we use water as a coolant, because it takes 4,200 joules to heat it up by a degree. So, as a coolant, it's brilliant because it can absorb an awful lot of heat before it boils, which is a good thing when it's cooling something down. When we're trying to heat it up to make a cup of tea, then it's a bad thing. It means we need more energy. So what is power? Power is work divided by time. The more work you do in the shorter length of time, the greater the power you have. Are you a powerful person? Yes, I do a lot of work in a very short amount of time. No, that just makes you someone who works at McDonald's, I think. Anyway, power is work divided by time. In this case, we've had the work from the previous question. The amount of energy taken in by the water is the same, so energy converted is the same as work done. Over the time it takes, it's 5 minutes in this case, to do the heating. Therefore, the object must have had a power of 560 watts. When I do the watts joke, it's not really funny when I do it in recording. Maybe it's not very funny when I do it in the classroom. I have to examine myself here. Am I funny? Yeah, of course I am. Right, so latent heat. Heat that changes state without changing temperature. So, where M is the mass of the body and L is the specific latent heat, it's exactly the same. Specific latent heat, specific because it's just 1 kilogram. You're trying to boil 1 kilogram. Whereas the latent heat is just to boil anything. I mean, I have a latent heat. I mean, a thimble has a latent heat. Everything has a latent heat, but specific latent heat is 1 kilo of a material. So 1 kilo of me would have a specific latent heat. That sounds a bit like, Merchant of Venice, the pound that lies closest to the heart. Boil it off a bit, lad. Boil it off. There we are. Oh, I didn't realise I did a slide about this. Amount of heat to change all the water into steam. That's latent heat. Now, some of you may have watched my kettle experiment. I hope you did. If you don't, go back and watch it, about how to use the electrical method to find specific heat capacity of water. Very good experiment, even if I do say so myself. Well, I've generally got a very good impression of how clever I am. But a kettle doesn't boil water. It brings it to boiling point. To boil water means to turn it into steam. So all the water would disappear in its liquid form and form steam gas in the room, which of course it doesn't do when you boil the kettle. So I'm not saying, of course we still say boil, but what we mean is bring to boiling point, to be really specific. And that's why we don't need latent heat when we're doing a calculation on kettle heating, because it isn't changing the state. Here's an example, together with one of the most, light on his feet steel workers I ever saw in my life. Oh, be nice. Basically, if you're going to boil something, that's one thing. But melting is also, melting or latent heat fusion is also something. We use the formula, of course it's in the logbook, and we simply multiply the number of kilos by the specific latent heat of fusion. This is it, the specific latent heat of fusion of copper, and we find out how much it is. Now, if you want to compare that in number size to the numbers we were dealing with earlier, you'll notice it's much, much bigger, up to 1,000 times more energy to melt something than just to heat it up. Now, it's not quite a good comparison, because when we're heating up, we're only talking about heating up by a few degrees, whereas here we're actually melting it. But there is usually much more heat required to melt or boil something than to heat it up between those two phases. That's common across all of physics and all of material science. So, here's an example. You freeze a bottle of wine by accident. You come in, I've got some white wine here. It's warm. Well, put it in the freezer. Put it in the freezer for a few minutes. Anyway, 2 days later, you open the freezer and there's your frozen bottle of wine. Oh dear, I forgot about that. Yes. So how have you frozen the bottle of wine? Well, the bottle of wine starts off at 20 degrees. You put it in the freezer. First of all, it has to cool to 0. Then it has to freeze, and then it cools to the temperature of the freezer of -10. Now, all of that is 3 different actions using 3 different calculations, because the constants, the specific constants for these things are all different. Let me try and explain. When you cool it down, of course, use the first one, Q equals mc delta theta, because you're just cooling it. There's no change in state. Now, I've used mass as density times volume. All those people in chemistry will be used to that. If you're not, get used to it, because of course, if density equals mass over volume, then we just Move the volume up there, and mass equals volume times density. There you are. There's a free bit for the chemists. That's change of temperature, of course, which is 20 degrees, because it was at 20 degrees when we put it in the freezer. It's got to go down to 0 to melt. Not melt, freeze, solidify, whatever word you want to use. So this is the amount of energy to do that, to get it down to the 0 before it started to turn into a solid. Then we use a different calculation, QML, for it to turn into a solid. The latent heat of fusion is that, and it works out to be that. Now, if you can see, it's already more. There's a lot more to freeze it than there is to bring it down to freezing. And finally, we have got to then turn this frozen solid at 0 to a frozen solid at -10. A 10-degree difference. There we are. 10-degree difference. Now, it's interesting. The specific capacity of the wine when it's frozen is different from that as a liquid. So the solid and the liquid are different. They're the same materials, but they have a different specific heat capacity as a liquid to that as a solid. And this is quite common. Water, it's about half, 4,180 for liquid water, but only 2,100 for ice. So very interesting. We add them together. And then how long does it take to do it? Well, it was, what is it? I don't know, 100 seconds? That seems... No, 100 watts. That's it. So you've got the number of joules it takes. The fridge works at 100 watts. You divide by the 100 watts, it gives you the time. That's what you see. You see, whenever you're looking at the number of amount of time in physics, quite often you divide the total amount you have by the amount that happens every second. So total amount you need is 410,000 joules. But the fridge works at 100 watts, which is the same as saying it converts 100 joules per second. So you divide by 100 and you get 4,100 seconds, which is the number of seconds, 1.13 hours, it takes for the wine to get to the state where it's undrinkable. And the bottle to break, probably. Measurement of specific heat capacity by electrical method. This is it. This is the joule meter. That tells you how much energy you're putting in. And the thermometer and the weighing scales tell you how much you're getting out. And then the only unknown is C. You see, there we are. That's it. That's the difference in temperature. That's C, which you're looking for. That's the unknown. That's the mass of the block. That's from the joule meter. And that's all because energy supplied equals the energy gained. And the most important thing to remember about all of this is you have to include some lagging. Lagging. Now, you can do it also for a liquid. Get the same result. The only difference is, of course, now we've introduced the calorimeter, which the liquid is in. Now, you could do it in a polystyrene cup, in which case that goes. But if you haven't done it in a polystyrene cup, then you have to include the mass of the calorimeter, C for the calorimeter, usually copper, and the change in temperature. And as I say, lagging, but also this idea of cooling the water. Now, why is that important? Well, supposing that is room temperature, and you go from cold to hot, well, then you cross between the two. You make the water slightly colder, so at the end it's slightly hotter. And then any heat lost when it's above room temperature will be balanced by heat gained below room temperature. They cancel each other out. So you slightly cool the water. So any heat lost above room temperature will be balanced by any heat gained below room temperature, and this will decrease the percentage error of the experiment. The other thing you can do is a method of mixtures, which is another experiment I very, 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 want to do and haven't got a clue how I'm going to do, but it looks simple enough. It's just you really need a thermometer for this one, and a very sensitive one. I've already thought I might be able to use the body thermometer for this, so rather than me having to get in the water or use a bath or something, it's just the metal heating up I want. I was hoping to get a horseshoe from somewhere. I thought that would be funny. But I can't believe how difficult it is to get a horseshoe when you're in lockdown. Short of running out and mugging a horse, I can't think of any way to do it. Anyway, the basic idea is you heat up some copper rivets until they're at 100 degrees, but in boiling water. And you leave them in boiling water a few minutes so you're fairly sure they're fairly close to 100 degrees. And then you quickly pour them into a calorimeter. And the calorimeter gets slightly warmer. And it really is only a few degrees. And you basically use this to work out the specific heat capacity of the copper rivets. Now, the most important thing to remember about this experiment is that to find the mass of the copper rivets, you take the weight of the calorimeter and the water before you add them, and then the weight at the end after you've added them, and you subtract them. You take the weight with a digital scale. That's the only way to accurately find the mass of the copper rivets, because it gets stuck on the inside of the test tube. They're difficult to weigh compared with the test tube itself. There's all sorts of different problems. So very best thing to do is to weigh them before you add the rivets and weigh them after you add the rivets. Rivet, rivet, rivet. There's a frog in there somewhere. Okay, so when we've done that, we still have the basic idea that heat lost by the rivets is equal to heat gained by the water and the calorimeter. This is the rivets, this is the water, this is the calorimeter. And of course, again, if you do it in a styrofoam cup, you don't need that one. Now we get on to latent heat. Latent heat, or the hidden heat, that's what latent actually means. It means hidden. Latent heat. Ah, it's latent. Yes, latent. Latent, you know, anything latent is hidden. Anyway, so latent heat is hidden heat. So you crush and dry some ice. You crush it so it's all at 0 degrees, and you dry it so that no water gets into the experiment, which has already gained its latent heat, and therefore will destroy the accuracy of the experiment by greatly increasing the percentage error and reducing the accuracy. That's it. That's what I say. So you put it in. You've slightly warmed the water, not to melt the ice quicker, but so that, again, any heat lost above room temperature will be balanced by the heat gained below. And the more ice and the bigger temperature difference you get, usually the more accuracy you can achieve with this experiment. The bigger the temperature difference on a thermometer usually means a bigger, more accurate experiment. So any large measurement is a smaller percentage error. If you have a very small measurement, then the percentage error is always going to be greater. So a couple of degrees, a couple of centimetres is always worse than 20 centimetres, 50 degrees. It's just a fact of life. So the larger the measurement, the greater the percentage error. And this is essentially why we draw graphs, because it gives a greater weight to the larger values higher up on the graph. It's called a weighted mean system. By this way, we can sort of like get a better average, because we ignore differences lower down near the 0, 0, because they're small numbers and they have a greater percentage error. Okay, this is the whole thing. Now, as again, I don't know, we've discussed on many occasions ways to try and remember this formula. If only that word meant something, then, or had a definition of some sort, or even was an acronym, I think it would be wonderful. Unfortunately, it doesn't, so we're just stuck with the word MILF. So this is the MILF formula. We have, first of all, this is the amount of heat to melt it. This is the ice turned into water, heating up to the final temperature, the temperature at the end of the experiment. This is the heat being lost by the calorimeter. This is the heat being lost by the water. The two of them, we have to assume, heat gained by the ice in melting and heating up must be the same as lost by the calorimeter and the water, or else we can't really do the experiment. Here's the same experiment for steam. Instead of crushing and drying the ice, we have to dry the steam using a steam trap, but everything else is essentially exactly the same, with the lagging, the measurement of the steam by subtracting the weight before and after the experiment. The same 5 measurements as taken: temperature before and after, mass of the calorimeter, mass of the calorimeter and water, mass at the end, which is obviously includes the steam, and we can work out them all by subtraction. Yeah. Do we need to do that? No. Okay, yeah, well, exactly the same formula. MSLV probably means something in some language. Anybody listening, if it means something in Serbo-Croat, would you please tell me? I don't know. It certainly doesn't mean anything in any language I know. Not that I know any language doesn't consist mostly of vowels. I'm not very good on languages of consonants only. Okay, so this is the question I've set you. It looks very long. It's actually not bad at all. It's from 2016, so relatively recent. I hope that all of it will go. The temperature on Niagara Falls one's very interesting. What you've got to remember about the temperature on Niagara Falls, this is this thing over here, is that the potential energy, which is mgh, has all been turned into heat energy, which is mc delta theta. And if you can't see that the m's cancel at this distance, and then you've just got GH equals C delta theta. I hope that makes some sense and helps you work out. The rest of it's not too bad. Good luck with it. A lot of the calculation stuff is down at the bottom, which is for a heat question because it's not in the log table, except the formulas. Good luck with it. Enjoy.